common myth is that black holes act like giant cosmic vacuum cleaners, sucking everything in from across space. This is not true. If our sun were replaced by a black hole of the exact same mass, Earth would not be sucked in. It would continue to orbit in exactly the same path it follows today. Of course, life would cease to exist because the planet would freeze without the sun's light and heat, but gravitational capture wouldn't be the cause. Furthermore, a direct collision with a black hole is statistically impossible. The vacuum of space is vast, and the relative size of black holes makes them nearly impossible to strike for billions of years. The event horizon is a critical boundary around a black hole. It is not a solid surface, but the point of no return. Once anything, even light, crosses this threshold, it is trapped by the intense gravity. To understand this, consider escape velocity, the speed needed to break free from a body's gravitational pull. At the event horizon, the required escape velocity exceeds the speed of light. For Earth, crossing this boundary would mean the absolute end of our planet as a distinct entity. No signals can ever return from beyond this dark, gravity-warped boundary. When an object as large as a planet approaches a black hole, it faces extreme tidal forces. Gravity gets stronger the closer you are. The pull on the side of Earth facing the black hole is significantly stronger than the pull on the far side. This difference, known as a tidal gradient, acts like a cosmic stretching machine. It pulls the planet into a long, thin stream of superheated plasma. This process is called spaghettification. The planet is ripped apart at the subatomic level long before it ever crosses the point of no return. Before reaching the event horizon, a black hole is surrounded by an accretion disk. This is a swirling, superheated ring of gas and dust. The extreme friction in this disk generates lethal levels of X-ray and gamma-ray radiation. This energy radiates outward in all directions. If Earth were to approach this environment, this intense radiation would incinerate the atmosphere and surface long before the planet reached the point of no return. This death by accretion disk ensures that any planetary structure is destroyed by radiation far from the black hole's gravity. As Earth approaches the immense gravity of a black hole, space and time undergo extreme distortions. To a distant observer, the planet's clock appears to slow down. The closer it moves to the event horizon, the more significant this time dilation becomes. Simultaneously, light reflecting from the planet loses energy, shifting toward the red end of the spectrum. This is known as gravitational redshift. From the outside, the planet never truly crosses the threshold. It appears to freeze in time, becoming dimmer and redder until it eventually fades from existence. A black hole does not need to collide with Earth to cause a global catastrophe. Long before any direct encounter, its immense gravitational influence would begin to distort our planetary motion. Even a passing black hole acts like a gravitational wedge, pulling on the Earth with forces that exceed the sun's stable hold on our planet. As the black hole nears, our stable, nearly circular orbit becomes increasingly eccentric. Gravity warps our path, yanking the Earth away from its life-sustaining distance. This gravitational disruption leads to two primary fatal outcomes. We are either thrown into the freezing dark of deep space or accelerated into a terminal spiral toward the sun. The mere presence of such an object is enough to undo billions of years of orbital stability. Once the event horizon is crossed, all paths lead to a single point, the singularity. Here, matter is crushed to a point of infinite density, where the laws of physics as we know them break down. Some theorists speculate about white holes, hypothetical gateways where matter might emerge in another region of spacetime. This suggests a potential bounce instead of a total collapse. However, current scientific evidence points only to the total destruction of physical structures. There is no empirical data supporting these gateways. The singularity remains the ultimate limit of our physical understanding. The current scientific consensus is clear. The probability of a black hole encounter is effectively zero on any human timescale. Black holes are rare, distant, and governed by the same predictable laws of physics that keep Earth safe in our current neighborhood. We are not at risk of being sucked in. Our solar system is a stable, well-defined environment, perfectly suited for the life we observe today. While black holes remain nature's most intense engines of destruction, they exist far beyond our reach, ensuring the Earth remains safe in the vastness of space.